This video is about B1, components of a vector. Vector quantities such as displacement, velocity, acceleration, force, momentum can be represented graphically as an arrow, where the length of the arrow is the magnitude of the vector and the direction of the arrow is the direction of the vector. Algebraically, we can represent the vector as having a certain number of units in the x direction and a certain number of units in the y direction. And if it is a three-dimensional vector, it also has a certain number of units in the z direction. Here you can see unit vectors I and j. I has a length of 1, or a magnitude of 1, and is in the direction that is horizontal, the x direction. And j is a vector with the magnitude of 1, which is in the y direction, or the vertical direction. Importantly, these two components have been chosen so that they are at right angles. In most situations, an effect which is acting in one direction will have no influence on the phenomenon in a perpendicular direction. For example, if I consider a ball moving through the air, its weight is acting down, and if there is the only force acting on it, the weight, then the acceleration on the ball will be down, and there will be no change in motion horizontally. Of course, this is unrealistic because in the air there is air resistance providing a horizontal force. We can use Pythagoras to find the magnitude of the vector A from its horizontal and vertical components. The square root of the sum of the squares of those two perpendicular displacements is the resultant displacement, or force, or acceleration, or whatever the vector is representing. A direction of a vector is usually given as an angle anti-clockwise from the horizontal. And so here is a direction marked with an arrow showing how the angle is increasing. Using trigonometry, we can find the value of x and y using sine and cosine of that angle, as you can see on the screen. Conversely, if we want to find out the direction of the resultant vector A, we can use arctan of the ratio of those lengths, as you can see on the screen. As long as the two components are chosen to be perpendicular, then we can use our sine, cosine and tan functions. And we can use Pythagoras. So it is very handy to make our components perpendicular. But it's not always useful for our vector components to be exactly horizontal or exactly vertical. For example, we might have a situation where we have a trolley on a ramp. It's a very common situation physicists find themselves in. Now suppose there is no friction and we want to find the acceleration of this object as it rolls down the ramp. We know the weight of the object, mass times gravitational field strength, will be acting directly down from the centre of mass. And to avoid any complications with rotational dynamics, let's assume that this body is a point particle. We have to select two components of this vector, and it is useful to have those two components so that one of them is parallel to the ramp. After all, we are after the acceleration parallel to the ramp. So here I have chosen my two components, which as you can see are perpendicular, where the blue arrow is the acceleration down the ramp and the green arrow is the component of acceleration which is perpendicular to the ramp. And I suppose what I should do is change my weight vector to just an acceleration vector down, because I'm not particularly interested at the moment in what that force is. But the gravitational acceleration down has two components, the component parallel to the ramp and the component which is perpendicular to the ramp, which I'll just label B. The angle I've drawn here is the same as the angle of the ramp, and you can see that by investigating the angles in these two intersecting triangles. So the acceleration component that is down the ramp is g sine alpha. When you are asked to give a direction which is a bearing, so a geographical direction instead of simply a vector, then we need to give a direction using the bearings system, where 0 degrees is due north, 180 degrees is due south, 090 degrees is due east, and 270 degrees is due west. The cardinal point northeast would be 045 degrees. And you can fill the rest in from there. My number one piece of advice to you is to draw a diagram, because other than drawing a diagram, as long as you have these 4 basic rules of trigonometry, you can answer these vector problems.